All right, let's get started with 9.4, mathematical induction. So what we're basically doing here is the pre-calculus version of geometry proofs. We're going to prove some statements are true here for sequences and series. So if you think back, there was an example 5 in section 9.2 that had a formula here, and it was 1, and then 1 plus 3, and then 1 plus 3 plus 5, and then plus 7, and we were always adding 2. Once we started with 1, we were adding 2. Right, so this is our extended formula here, 1, 3, 5, 7, 9, and then all the way up to whatever 2n minus 1 happens to be. So, but if you get the answers to them, you'll find that it looks like the answers follow a pattern. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So it looks like the sum is always going to be n squared, right? If n is 4, the answer is 4 squared. If n is 2, the answer is 2 squared. So we think that the answer to this, the shortcut for this, the formula for this, is n squared, right? But we can't just look at the first couple and say, yeah, the first couple work, we're going to go with the formula. Because there's lots of, and there's actually in the book a long example problem of one that doesn't work. It works for the first few, but then it breaks down. Okay, so we can't just jump to the conclusion that our formula works. We have to prove it. And so here's how we're going to prove it with the principle of mathematical induction. Here's how it works. If we can prove that the first number in our list is true for our formula, and then every consecutive option after that, every positive integer after that works, so k plus 1, this is our recursive stuff we were talking about, the next one in the list works, then all of them must be true. All right, so we have to prove two things this section. P1 is true, the first number in our list is true, and the next number is true. Okay, so we're going to substitute k plus 1 in for n, and you'll see how that works here. But first things first, let's just do substituting, not proving yet. So for a, what does it mean to substitute k plus 1 in for k? Everywhere you see a k, write a k plus 1. So for a, k squared becomes k plus 1 squared, k plus 1 becomes k plus 2 squared, all over 4. For b, the formula is 1 plus 5 plus 9 plus dot 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 plus 4. K minus 1, we're going to replace k with k plus 1. So plus 1 minus 1 just turns into k minus 3. You'll notice 4k minus 3 is what the next one in the list is, so that should actually work out. And then the next one is going to be 4, got to substitute in k plus 1 for k, minus 3, that's 4k. And then plus 4 minus 3 is plus 1. All right, so that's the substitution there. For c, k plus 1 plus 3 is k plus 4 is less than 5 k plus 1 squared. For d, everywhere we see k, we go k plus 1 is greater than or equal to 2k plus 1, otherwise known as 2k plus 2, plus 1 more gets us 2k plus 3. All right, so everywhere we see k, we're going to substitute in k plus 1. That's our rule here for induction. See if you can simplify here for 5, figure out what p of k plus 1 is if you're given p of k. Okay, so now we're going to move into the proof side of things. So all of these proofs have 2 steps. First step. Step 1. Prove first case. All right, so the first case here is we think that this long equation turns into n squared, right? This is from the original example. Let's prove it. All right, so job 1 here is to prove that the first one, the first case, 1, is equal to whatever our formula is if we plug in 1. So plug in 1 for n, Is 1 equal to 1 squared? You betcha. That's the easy part. Step 2, a little bit longer. So step 2, prove the k plus 1 case. So everywhere we see k, we're going to substitute in k plus 1. Now in this example, we have n, so we're going to use n plus 1. Same deal though. So b, we're going to say, okay, 1 plus 3 plus 5 plus 7 plus dot, dot, dot. And then we're going to go all the way out here to the end. We're going to say plus 2n minus 1, what we had before. Now we need to add on one more case. And the next case here is going to be 2n plus 1 minus 1. So that's going to turn into 2n plus 2 minus 1. So plus 2n plus 1. All right? Does that equal, instead of n squared, does that equal n plus 1 squared? All right, so now here's the nice thing. We already assume what this is equal to. We're going to assume that our theory is right. We're going to assume that this whole thing does equal this. And we're going to see if that works. So we're going to substitute for this whole part n squared plus the 2n plus 1 from here. That goes there. Does that equal n plus 1 squared? All right, so n squared plus 2n plus 1, we can factor that. That's n plus 1, n plus 1, and that's n plus 1 squared, which does indeed equal n plus 1 squared. So we have proved that this is the true formula because we proved the first case and we proved the k plus 1 case. So that's what you need to do here for example 11. Give it a shot. Okay, so let's try one more here. So using mathematical induction to prove this. First case is 1 squared, that's the first one in our list, equal to plugging in 1. Everywhere I see n, I'm plugging in 1. 1 times 2 times 2 times 1 is 2 plus 1 is 3 over 6. 1 times 2 times 3 is 6. Divided by 6 is 1. Okay, we got that one. Let's do the n plus 1 case. So 1 squared plus 2 squared plus dot 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 n squared plus, we got to add on the n plus 1 squared case. Does that equal, change all your n's to n plus 1s. n plus 2, 2, n plus 2 plus 1, so 2n plus 3. All over 6. Okay, what does this whole part equal? We think that it equals this, so we're going to substitute it in. n plus 1, 2n plus 1, all over 6, plus this one here. And I'm just going to make it 6 n plus 1 squared over 6 so that we can have a common denominator. Does that equal n plus 1 times n plus 2 times 2n plus 3 all over 6? Let's find out. All right, since we have a common denominator, we can get rid of all these denominators here and just try to prove the numerators are equal. And so let's see what we've got here. We've got, now one thing I notice here is there's an n plus 1 in both of these. So we can factor that out. N plus 1 factors out front. What are we left with? We're left with n times that, so we're going to have 2n squared plus n plus 6 n plus 1. Okay, just going to clean up the left side here, n plus 1, and then we've got 2n squared plus 7n, 1 plus 6 more, plus 6. And let's see if we can factor that. N plus 1. That's going to be 2n just trying to factor this and 3 right here and a 2 right here. And look what we've got. N plus 1, n plus 1, n plus 2, n plus 2, 2n plus 3, 2n plus 3. Our job here is done. We've proved the left side equal to the right side. Your turn. See if you can prove 17 is true. Okay, so now we're going to use the extended version of this where we got some inequalities. Okay, so if you're going to prove that n is smaller than 2n, we need to prove the reverse of that. It's oftentimes easier to say greater than. So let's prove that 2n is greater than n. All right, so first case first. This is the easy one. Is 2 to the first greater than 1? Plugging in 1 for n. 2 is greater than 1? Yep, checks out. All right, so now we need to do the extended version. 2, instead of n, we're going to put n plus 1. Is that greater than n plus 1? That's what we need to figure out here. Okay? All right, so as we walk through this, what we can do here is, if we can prove that 2n plus 1 is greater than something, which is greater than something else, which is greater than something else, which is greater than n plus 1, we'll have proved that it all works out. Okay, so we need to see if we can split this up and figure out what this is greater than. Okay, so 2 to the n plus 1, another way you could say that is 2 to the n times 2 to the first, because remember what we do with the exponents is we're going to add these up together. Okay, so we know that that is greater than 2 to just the n, right? Because we know that 2 to the n times 2 has got to be greater than 2 to the n, right? So we know that we're bigger than 2 to the n, all right? 2 to the n, exponents are going to be bigger than multiplying, so we're definitely bigger than 2 to the n, and that'll actually get us all the way to the end, because 2 times a number is bigger than a number plus 1, as long as that number is bigger than 1. So we've got the whole chain, it all works out, and our job here is done. All right, so with inequalities, you're going to do a string of inequalities all the way down. See if you can put that together. This is probably the most complicated for me, this set of inequalities. So do your best here, try 25, answers coming in a second. All right, another tricky one here is seeing if we can prove that 3 is a factor of this. All right, so let's prove the first case. First case is straightforward. Is 3 a factor of 4 to the first minus 1? 4 to the first is 4 minus 1, which is 3. 3 is definitely a factor of 3. Okay? All right, so now what about the 4 to the n plus 1 case? Okay? All right, so what does 4 to the n plus 1 really mean? Okay, so on this one, we can split that up into 4 to the n times 4 minus 1. Okay, and there's a reason that I'm going to put the minus 1 over here, because I know that 4 to the first minus 1 works. Okay, so I'm going to sneak in a 4 to the first right there, because if I do that, I know this works. But I can't just magically throw something in. So if I'm adding that in, I would need to minus it as well. Okay? All right, so we know that this portion here works, 4 to the first plus 1. And if I add that to a factor, it's still going to be a factor. So now I just need to prove that this portion here is a factor of 3. All right, let's see if we can do that. If we have this, then we're going to have 4 to the n minus 4. So we can pull out a, what are we looking at here? Let's see, did I make a, yes, sorry, 4 to the n and 4 to the n minus 1. We're assuming that's correct, right? So we can have that in there. If we have 4 to the n times 4 minus 4 to the n. We can pull a 4 to the n out. And we're left with 4 minus 1. 4 minus 1 is 3. Anything times 3 is by definition a factor of 3. So we've just proved this part works as well. So at this point, our job is done. We've proved that 3 is a factor of 4n minus 1. See if you can use similar thinking here. I know this gets a little convoluted and confusing. We'll go over it in class, but do your best. See if you can prove that a factor of n cubed plus 3n squared plus 2n has to be 3. Okay, so now the next thing we're going to look at is what if you're given a pattern. Your job is to come up with a formula for it, and then your job is to prove that it works. Okay? So what we're going to look at here is, here's our formula. The first thing we're going to do is we're going to figure out the first couple of terms. So what about the first one? That's just 1 over 1 times 2, which is 1/2. What about the second one? That's 1 over 1 times 2 plus 1 over 2 times 3. So we know that's a half plus a sixth. So that's a 4/6, which is 2/3. Do one more here. We know that this is going to be 2/3 plus the next one, 1 over 3 times 4 is 12. So that's going to be, how many 12ths here? 8 plus 1 more is 9/12, which is 3/4. And at this point, I think you can see what the pattern might be. S sub n, it looks like, is going to be n over n plus 1, right? If n is 3, then 3 over 3 plus 1. If n is 2, then 2 over 2 plus 1. All right, we think that might be the pattern. Let's prove it. All right, S1, right? So is this equal to plugging in 1? 1 over 1 plus 2 is equal to 1 over 1 times 2. I'm sorry, not 1 plus 2. I got carried away. 1 plus 1. 1/2 equals 1/2. We've proven the first case. Let's prove the n plus 1 case. Okay, so we've got this whole list. And I can actually erase this just for some space. Let's just use this already. O plus 1, n plus 1. n plus 1 plus 1 is n plus 2. Equals to, what do we think the formula is? We think the formula is n over n plus 1. So the n plus 1 case would be n plus 1 over n plus 2. Move that out of the way. Let's see if we can do that. We assume that this whole portion is equal to n over n plus 1 plus 1 over n plus 1 n plus 2. Let's prove that that's equal to n plus 1 over n plus 2. Okay, we need a common denominator on the left. N plus 2, n plus 2. So now we've got n squared plus 2n plus 1 all over n plus 2n plus 1. The numerator can factor. That's going to be a perfect square, actually. That's n plus 1 times n plus 1 all over n plus 2 times n plus 1. And I think you're going to see what happens here. Cancel them. N plus 1 over n plus 2 is equal to n plus 1 over n plus 2. So we have proved that this is correct. Your term. Last one you're going to have to do like this. Okay. Take a moment. Pause this. Write this down for a second. The sum of the powers 1 through n is this. The sum of the 1 squared through n squared is this. Okay, these are proven formulas. Cubing is this, to the fourth is this, to the fifth is this. You're not going to have to memorize them. Write them down, have them at your disposal though. Okay, so now we're going to find each sum using these formulas. So this is I cubed, okay? So we could add them all up. I don't want to do that though. I want to use the formula. So the I cubed formula is n squared, n plus 1 squared over 4. In this problem, n is going to be 7. So 7 squared times 7 plus 1 squared all over 4. That's 49 times 56. 56 times 64, sorry, over 4. And 49 times 64 over 4 turns out to be 784. Second problem. Okay, so we have a couple of formulas from a couple chapters ago where we can split these summations up. This is going to be the sum of I equals 1 to 4 of 6i minus the sum of 1 to 4 of 4i squared. And we also have a formula that says the 6 gets to come out in front. And this is very helpful because we have a formula for I. The 4 comes out in front. And we have a formula for I squared as well. The formula for I is n plus 1 over 2. Times 6 out front minus 4. The formula for I squared is n plus 1, 2n plus 1. All over 6. Okay, so let's plug them in. N is going to be 4. So let me write this right here. 6 times 4 times 5 all over 2. Nope, minus 4. 4 times 5 times 9 all over 6. And let's see what we've got here. 4 times 5 is 20 over 2 is 10. So 60 minus 4 times 5 is 20 times 9 is 180. Divided by 6 is 30 times 4 is 120. Negative 60, I think. Let me check. Aha, yep, that is correct. All right, use those formulas. Split these up, see if you can figure out 55. Okay, last thing here. Finite differences. If we have a sequence, 3, 5, 8, 12, 17, 23, there's a quick check to see whether it's a linear or a quadratic formula. What we're going to do is we're going to find the differences between the numbers. 5 minus 3 is 2. 8 minus 5 is 3. 12 minus 8 is 4. If all of these numbers, the first differences, are the same, it's a linear model. If not, subtract them again. 3 minus 2 is 1. 4 minus 3 is 1. 5 minus 4 is 1. 6 minus 5, they're all the same. If the second differences are the same, you have a quadratic model. All right, so in this case, it's a quadratic model. And so we're going to be able to figure out what that model is using substitution. So here, we know that this is 2. We'll just put these up again. 3, 4, 5, 6. So the second difference is 1, 1, 1, and 1. So we know that, let's see, what do we got here? We write it in the best way that makes sense. We know that we've got ax squared plus bx plus c is our quadratic model, right? Okay, but we do have in here, the first term is 3, the second term is 5, the third term is 8. We've got enough here to figure out what is a, b, and c, okay? So if x is 1, the answer turns out to be 3. If x is 2, the answer turns out to be 5. And if it's 3, if x is 3, the answer turns out to be 8. All right, so rewritten here, this is going to be A plus B plus C is 3. 4A plus 2B plus C is 5. 9A plus 3B plus C is 8. And so we could use some elimination and solve this going through it, okay? I'm not going to go all the way through it because I'm not going to actually ask you to solve these, okay? You can check the example in the book. We're going to focus on are things linear or quadratic just using the first and second differences, okay? There may be an extra credit problem for solving the linear one, and we can talk about that in class. Okay, but for now, I just want you to find the quadratic model. Okay, just take a look at this. I just want you to really look at the solution here, okay, because they go through all the elimination. Don't spend your time solving this all the way through, but just kind of take a look at the example and make sure that this kind of makes sense. All right, we'll go over the rest in class. Any questions, make sure they're answered, and good luck with everything you try.